When we used to have the first, so to say, motivation talk on the quantized vibrations at the beginning of the week on Monday, there we did discuss examples in physical chemistry, what can oscillate, and we did formulate the Schrödinger Hamiltonian and Schrödinger equation for oscillations. Now we do have a mathematical problem in front of us, and the goal is to solve time-independent Schrödinger equation and find energies and wave functions. Or in what follows, we will seek to solve time-dependent problem. When we were considering the key to homework, last homework, extra credit number, whatever, problem number 6, we already considered how the center of the distribution, how the expectation value of position and momentum are moving forward in time, but it is very far from where we are now. We need to meticulously cover some basic aspects. And the I see that there is nothing entertaining on the screen, which is not good. Let's bring at least something. So we are going to use a shortcut. The problem that we are going to solve is not a regular linear differential equation, because it increases derivative of the unknown function, and not the unknown function times constant, but unknown function times independent variable. And the solutions of such problems typically do not have answers in elementary functions like exponential, sine, and cosine, but have answers in special functions, which are defined as function to solve this equation. We are going to this problem can be solved by series expansion, and it is doable with our knowledge of calculus, but it will be boring. I'm going to select a bypass, which previous years I was motivating everyone that it will be shorter, but it will be not shorter, it will be about the same way, but it will give me chance to speak rather than derive equations. And it will be more philosophical way to solve this problem rather than doing a lot of calculations. So the title is ladder operator. So it will be a new concept. Oh, we should have started voting. Can we postpone it to Monday? I should send maybe the examples from previous years so that you can slowly start preparing and selecting what you want. If I forget doing it by like night, please remind me, and I'll share material so that you feel more comfortable preparing. Okay, so here is the summary of the last lab, if you were missing it. So we were considering how to represent momentum operator in basis if the wave functions are represented as a set of discrete values, and momentum operator is concentrated along main subdiagonal having opposite values. And this is a main part of the code that we are going to practice, which also uses this momentum operator towards Hamiltonian and evolution operator. So here is the equations that we need to solve. The term here is just the second derivative, which represents kinetic energy. And next term is potential energy, which is second power of the elongation. So we got it last time as by expanding potential energy surface in vicinity of equilibrium, right? So this R squared term makes our life difficult, and in standard way that you'll find in textbooks if you open them, typically one is making a transformation to represent the unknown function as decaying as a Gaussian exponential times set of polynomials, polynomials like independent variable plus independent variable square, like Taylor series with unknown coefficients. And then one is trying to plug it in and find coefficients. We are going to use the method which is referred to as ladder operator. And by applying this method, we will get, by today, we will get a ground state, which will be Gaussian function above the center. And when we meet next time, we'll get the rest of all the functions. So here is something that is illustrated with ugly drawing, but there is a chance that some of you may enjoy it. So remember our old friend Stroman, who helped us to get through the concept of density of states. So there we used it to watch the number of states. Now, so it was moving along the counted eigenstates and looking for certain energies before and after energies, right? Let's try to think in a similar way. Suppose we have already found the eigenstates, and they will be arranged. We can order them in energy. Lowest state lower, highest state higher, and then in ascending order. And then we can set up an operation of jumping, climbing a ladder, going one state up, 2 states up, 3 states up, or going only 1 step up or 1 step down. Is it possible? Right? So we can, instead of us, we can tell it is a straw man who is walking through the stairs. And now there is think that some of you may, I do not exclude it, may find beautiful. So suppose we found that through all energy states, there is a minimal one, right? In particle in the box, we already had the ground state, which has energy a little more than 0, but there is nothing below it. And the justification is that kinetic energy is always positive, and if there is potential energy is also positive, their summation will be positive. Now, let's employ the strawman who can climb up and climb down, and then we give an order to the strawman to jump down from the lowest stair, from the ground floor. So, what do you think about the possibility of such operation? Like, if I'm your subordinate and you tell me like, go down through the floor, what do I answer?
I think Stroman would just be very frustrated that he wouldn't be able to go through the floor.
Okay. So do you think it is possible or impossible?
I don't think it would be possible, no.
Okay, so it will be impossible, right? And if a mathematical operation is impossible, what is the probability of such event? Okay, yeah, thank you, Nate. So this is main idea of today's meeting, and I am very happy to observe that you follow it. So if we have set of eigenstates, we can call them phi 0, phi 1, phi 2, phi 3 with energies which are ordered in ascending way, E not E1, E2, E3, and we have operations like of climbing up, climbing up, climbing up, in the operation climbing down. So if you climb from number 3 to 2, we can climb down from 2 to 1, from 1 to 0. And then if we give order to apply this climbing down operator to the ground state, it will not work. It will be 0, right? So there and going up and down is sometimes referred as creation and annihilation, because we create more energy and annihilate energy. But I want to declare that implementing this operation mathematically will save us, will not save us time, because we already spent time describing it and discussing, but it will save us time sitting and deriving equations. So this equation, after we implement it, will be simpler than this one, and it will be possible to solve in in 2 lines. Okay, and by so we need to express this annihilation ladder down operator in terms of differential operators, apply it to unknown function, and find this unknown function. And the answer was already declared. It will be a Gaussian shape. So this is a plan for the activity today. There is another consideration for building this operator. What do we have? What do we include into the total energy operator, into Hamiltonian? Which component? Kinetic and potential. And if our main variables are position and momentum, how does total energy depends on momentum? Yes, but if instead of differential operator, we just have a standard like momentum as a variable. Like how kinetic energy is expressed through velocity.
Mass times velocity squared.
And through momentum.
Well, momentum is mass times velocity.
Yes, so
Right.
kinetic energy is,
The velocity squared.
or in terms of momentum, if velocity is momentum divided by mass.
Yes.
So how kinetic energy is expressed in terms of momentum?
The square root of.
Not squared, momentum squared.
Yeah.
Okay, so momentum squared comes into kinetic energy. How the elongation, the coordinate comes into total energy for this specific problem.
I don't know.
Come on, you know, we had it. I just it was a trap that I moved to different slide, but we had it a couple of slides ago. So how the potential energy surface depends on position.
I guess I wasn't paying enough attention. I don't remember.
But can you draw in the air potential energy surface? You can. It is easy. Like draw a curve in the air. No. Can you make it going up? Okay, so it goes up if we elongate, and it goes up if we contract, right? Can you draw it? The function with minimum. Just draw it in the air. It starts high, goes down, and then goes up again. Yeah. And can you point a minimum in your air function? Yes. So if we go to the left and to the right, it increases. Can you express it as parabola, as elongation squared? Yes. So in which power coordinate comes into total energy?
Okay, it's quadratic.
Okay. Yeah. Thank you.
I guess.
Maybe. No. It was not a trap question. So let's try once again. So momentum and position, they are entering the total energy operator in which powers?
The second power.
Okay, yeah, thank you. So we all agree on that. And this a little, sorry for this interview, I just do not want to lose contact. Because if I mumble something and you don't care, then there is no reason to continue. So these two variables for this problem come into second power. And I want to connect it to our formulation of the ladder operator. There is another consideration which make it like appetizing and pleasant way. So if, yeah, it is here. If we go and it may not be explicitly told in textbooks, but it is an idea behind what is typically written. So if you do have several energy levels, and if you know that system is on a certain level, right? So if you go down so much and then back up so much, or if you go one rung up and one down, you will get the same energy, right? The energy will not change. And by this a little bit strange logic, one can say that applying the operator of climbing down and climbing up simultaneously should give us total energy. If you were considering to take notes, you may write it down or just think, because it is a little unorthodox thought. So we want to design this climbing operators going up and going down in such way that by multiplying them one by another, we will get total energy, we will get Hamiltonian. So we need to design this operator in such way that it will be equivalent to this total energy, which includes position squared and momentum squared. Make sense, or it looks very strange? Okay. So philosophically, going up and then returning down, you'll keep the same energy on one hand. Therefore, product of this operator with some coefficients and additional terms should give energy. And if we assume that these operators, this is like a assumption because it is not a rigorous problem. It is set up that helps human to deal with this problem. If we represent these operators as linear combination of position and momentum, and if we multiply these two linear combinations, then we will get a polynomial of these two variables with most senior power 2. Position squared and momentum squared. Better? Okay. And in some sense, I probably will skip some details because they're boring for you and me, but there is a way to solve this equation. So plug in these definitions with unknown coefficients p small p, p1, p2, m1, m2 for, and then solve them to find these 4 coefficients that these 2 lines will become equivalent. Select such coefficients which will make, and then after solving it, the values of these coefficients will be used to define these ladder operators. So we used maybe 3 concepts. One, that we just climb up and down, and climbing lower than ground floor is not possible. We borrow concept that Hamiltonian includes position squared, momentum squared, and then we use the concept that going up and down keeps the same energies. Therefore, these two things must be equivalent. And if you combine everything together, it will be a mathematical tool which gives us more token, more definitions, but actual mathematical challenge will become substantially simpler. So if I shut up and just derive by standard way, maybe we even will conserve some time. But if I'm doing it for the first time, there is a chance of error. And with these new definitions, everything will be at the pre-calculus level. Okay, creation, annihilation. The properties of these operators that they are conjugated to each other, and by applying conjugation, by swapping rows and columns, if they're matrices, rows and columns, and making complex conjugation, it will be original operator. So if you take operator for going up but apply conjugation, it will become going down. If you apply it twice, it will be the same. So here is what I will try to skim through it as quick as possible, but just show some steps of derivation so that in what follow you try to believe that it is correct. Or if you do not believe, you have some reference points to check. So we are going to put unknown coefficients here and there, and open these brackets and make sure it will be equal to the Hamiltonian. So in Hamiltonian, we do have only two terms, momentum squared and position squared. Here, by opening brackets, we will also have cross terms, position times momentum, right? And we have a zero energy term, which later on we can prove that it really exists, but it makes sense, and it is connected to a particle in the box where the lowest energy was non-zero, right? So find coefficients. And by plugging it in and trying to solve, one can do several manipulations and identify that coefficients in front of position squared and momentum squared will be equivalent to this coefficients, same coefficients for original Hamiltonian. So factor in front of momentum and factor in front of square of elongation. And for the cross terms and free term, we have a combination. So here I'm getting minus IH because I want to flip the position and order of position and momentum and practice their commutation so that I can use standard algebra. And by attempting to solve it, so from first and last, one can get the P1 and P2 coefficients, and by continuing this this solution, one can solve for all of them. Okay. Yes. So there will be two independent solutions, and then the M in front of minus going down will be just opposite and conjugated. And the values of these coefficients, which we can double check by solving will be one of them mass, and both of them will have square roots. One of them has they both have Planck constant and factor 2 in the denominator, and the different coefficients have mass and frequency of oscillations either in numerator or denominator. And also there is interesting property that by cross multiplying them, one is getting Planck constant and frequency, which will be comfortable to come into the shorthand equation for Hamiltonian. So if you plug these solutions in, we are getting the definitions of annihilation and creation operator. So they do have different imaginary part and different signs of in front of imaginary part, which will correspond to their property of being conjugated to each other. And the factor in front of position has mass and frequency in the numerator. The factor in front of momentum has mass and frequency in the denominator. By the benefit of this solution is that the operator itself is dimensionless. So this combination of factors compensate whatever dimensionality of position and momentum is, and the operator itself will be dimensionless. So we will apply it to dimensionless wave function and get again dimensionless wave function. So what was our plan and goal? So after we start believing that it is a correct equation, we want to give an order to a straw man, like to jump down to the floor. I would say we give an order to a straw man to commit a suicide, which he will definitely reject. So it means we need to take this operator, apply it to unknown psi naught function, and make it equal to 0, and see what happens. I declare that this equation will be solvable and will be as pleasant to do as solving differential equations can be pleasant at all, if anyone considers it pleasant. So the momentum can be replaced in terms of derivative. Then I believe I have multiplied each part by square root of omega, and then we get rid of omega here, and we get omega without square here. And we can immediately see that this equation has first power of independent variable multiplied by a known function, and first derivative over independent variable multiplied by a known function. So you can say that it is not much simpler than original function where we had second derivative and second power, right? But it is. So after we take care of all these factors and imaginary units here, the equation to solve will be r times phi plus d phi over r equals 0. Any ideas how to solve this equation? Please give me a sign if if you feel comfortable and can solve it by pen and paper right away. Or if you have some guesses and ideas what can be done. I can even stop recording if the ideas will be crazy. Just
Could you separate the variables? So put the psi function on the right hand side.
yes, it is. Yeah, thank you, Wyatt. It is a very healthy direction of thought. So we can. I'm just following the idea of Wyatt. So there are only two terms. We can put one on one side from equality sign, another to another side, and then we can any mathematical equation can be processed by multiplying or dividing by the same factor. So if we divide everything by phi and multiply everything by dr, then this term will depend only on phi. This term will depend only on r. And then one can apply integration over these different variables from different sides of equality sign, left and right. Make sense? Joe? Okay. So yeah, I think I was thinking the same way as Wyatt years ago, or maybe one of the class attendees did scratch it here. So put it on the other side, and then we will have this equation, right? Which is already, if you put just integration, it's already a solution. You just need to carefully process and write down the answer. So I lost my chance to approach you and ask this very complicated question. What is the integral of 1 over independent variable? You know it, right? What is the integral of the linear function? So you also know it. And it should be constant either here or there, doesn't matter. And then we just make these two things equal to each other and solve for phi, because phi is our independent variable. So if it is log on one side and no log on the other, we can use left and right parts as power of exponential. Like take exponential into the power of that stuff, and then exponential of log will be function itself, right? And then we will have exponential of this r squared. So this factor m omega over h comes from careful processing of the factors that I skipped, and exponential to the power of log of independent function will be independent function itself. The coefficient here will be responsible for additional factor in front. But by now, we do not know this factor. The way to find this factor is the same as we did in one of the homeworks. So we need to normalize so that the area under the square of this wave function will be equal to 1. So that if you decide to find any expectation values, they will be found in a reasonable way. And by taking care of the factors, one can get the width of this thing. So by now, we are getting a mathematical support that if we assume that oscillating ions do have quantum properties, if you just plug the spring constant and mass corresponding to oscillating atom in the atoms in the, let's say, diatomic molecule into Schrodinger equation, we will mathematically prove that even for the ground state, there will be a distribution of probabilities. So interatomic distance will have probability to be a little shorter or a little longer than the bond length. So it is the main observation from the solution. But we are going to continue this journey and get more properties. So defined at any elongation, whether it's short or long, centered at the bond length, it is similar to the Gaussian wave packet we used to study free space, and some properties can be inherited. And there is a similarity to particle in the box. So there is one peak corresponding to center of the potential, and the energy is bigger than zero. So here is another comment about why normalization is needed. So if our wave function is not normalized and we need to find expectation value observable for some observable, then this procedure to find expectation value must include dividing by normalization factor. Without it, if you do not perform this normalization, the value of observable will be multiplied by some random factor, and it cannot be compared to experiment. So if you have uncertain coefficient factor in front, but if you perform this operation, then we will have one and only one answer as soon as wave function is defined. And it is very comfortable to take, and it is not my personal idea, it is what people typically do. So this denominator is treated as a factor that can be added or multiplied to the wave function upfront. So if we find the value of this integral, take a square root and divide wave function by it. So if we redefine psi, maybe psi normalized as original psi divided by square root of this then this function will be normalized, and if we need to find expectation value, we do not need the denominator anymore. Make sense? So if one carefully processes this operation, which means we take the ground state wave function, multiply by itself. So it by multiplying by itself, it gets rid of this factor one half, and then we know that this is Gaussian integral, which will be equal to square root of pi if we process if you select correct independent variable. So if we redefine independent variable so that the stuff in the power of exponential will be just new variable u squared, then you get square root of pi. And this can be done by setting up u variable as square root of mass, frequency, and Planck constant. This will change the infinitesimal increment. And by performing this, what? No. By performing this operation, one would get that the normalization factor will be this stuff times square root of pi, and it should be equal to 1. And if we solve it for n, it will be square root of the combination of Planck constant, mass frequency, and pi. But I think this year we are going so much quicker than the previous than we finish earlier. So let me announce adjourn. Let's relax from the homeworks for on this weekend, because you did 2 homeworks due this week, and let's get ready to presentations. Just select your primary choice, and on Monday we'll do this procedure of voting. I intend to share some material so that you already start working on them. Okay, meeting is done. Have a nice weekend. If you have some questions, I'll stay here and answer, either online or in person. But if needed, everyone is welcome to disconnect.